I would imagine something that we've seen plenty of in our previous math classes is examples of both consistent systems as well as inconsistent systems. What I'd like to do in this video is talk about how to interpret a dependent system. A dependent system, by definition, is one that has an infinite number of solutions. Now, when you have an infinite number of solutions, the way that you represent that infinite number of solutions is significant. So first and foremost, I would like to introduce the concept of lead variables and free variables. A lead variable is defined as once you have a system in row echelon form, and we'll get into more details in that in a future video. A lead variable is simply the first variable listed in an equation. Now, generally speaking, there should be as many lead variables as there are non-trivial equations once you get down to this row echelon form. So, number of lead variables should be equal to number of non-trivial equations. Now, by non-trivial equations, I mean as you are going through the process of elimination, a trivial equation would be something that results in like a 0 equals 0. Basically, a trivial equation happens when you have multiple equations that are all saying the same thing. We can wind up essentially canceling out those equations by turning them into 0 is equal to 0. A free variable is any variable that is not a lead variable. So every variable has to be either a lead variable or a free variable. If you can't identify it as being a lead variable, it automatically becomes a free variable. So for your free variable or free variables, you are going to use what's known as a parameter. A parameter is a variable that represents any real number. Most frequently, the parameter that we're going to be using is going to be t. So we'll usually see this representation of that parameter. T is an element of the set of all real numbers. This is what this notation means. Now, the goal is to get our dependent system in terms of whatever parameter or parameters we happen to be using in the problem. If there's more than one parameter, like if there's a second parameter, I would recommend S, and if there's a third parameter, I would recommend R. Now, with those things in mind, let's actually take a look at a couple of examples of dependent systems and see if we can make use of this parameter notation. So here we have a system of equations. We have x1 plus 3 times x3 is equal to 7, and x2 minus 2x3 is equal to 10. The first thing that I'm going to do is point out where all my lead variables are. Now, lead variables, again, are supposed to be just the first variable that's listed in an equation. These are your lead variables. So lead variables are going to be x1 and x2 in this system. Then, anything that is not a lead variable is going to be a free variable. And in this case, that would be x3 is going to be your free variable. So the first thing we're going to do is we're going to parameterize our free variable. We'll say let x3 be equal to t. Then the goal is we're going to solve for x1 and x2 in terms of this parameter. Now, in order to do so, that means first we actually plug in the parameter. So it'll be x1 plus 3t is equal to 7, and x2 minus 2t is equal to 10. Both of these will be solved relatively easily by simply adding or subtracting the t term over to the other side, whatever happens to be necessary. So for the first equation, we'll get x1 is equal to 7 minus 3t. And in the second equation, we'll get 10 plus 2t. Now it doesn't matter if we were to write this as negative 3t plus 7 or 2t plus 10, that would be equivalent results. So the solution of our system, we have a couple different representations that we could use. One of them would be simply, this is the set of all ordered triples, x1, x2, x3, such that x1 is equal to 7 minus 3t, x2 is equal to 10 plus 2t, and x3 is equal to t, where t is an element of the set of real numbers. So, just expressing this as ordered triples and then explaining all the things that we just said over here. Sounds like my cat is getting into my bed. The other possibility, of course, would be to cut out the middleman and just go straight into an ordered triple, where instead of calling it x1, we'll just say that it's equal to 7 minus 3t. Instead of calling it x2, we'll just call it 10 plus 2t. And instead of calling it x3, we'll just call it t, where again, t is an element of the set of real numbers. If I had to give a preference to one of these, I would probably say the bottom one, just because it's shorter and more concise. So with that in mind, let's try out another example. This one will be in row echelon form, but not what we refer to as reduced row echelon form. So once again, we're going to start by identifying lead versus free variables. x1 is the first one listed in the first equation, and x2 is the first one listed in the second equation. These are our lead variables. I just realized that I reversed the color scheme from the last problem. Sorry about that. And then we've got our free variable in the form of x3. So with those things in mind, let's go ahead and define our parameter for x3. Let x3 be equal to t. Then we would be looking at x1 minus 2x2 plus t is equal to 0. And we would also have that x2 plus 1/3 t is equal to 2. Now the second equation I can solve in terms of t no problem, but the first equation is going to require some additional work. So first we'll say that x2 is going to be equal to 2 minus 1/3 t. Now the reason that the first equation is going to require a little bit of extra work is because it still has an x2 in it. So let's take this and put it up here. This will be x1 minus 2 times the solution that we just got for x2. We'll plug that in as well. So 2 minus 1/3 t plus t is equal to 0. This one's going to require a little bit of extra algebra, but hopefully we'll get there with the very limited space that we have left. I did not space this one out particularly well. So this will be x1 minus 4 plus 2/3 t, once we distribute that minus 2 through, plus t is equal to 0. You can combine these two terms into one single fraction. 2/3 t plus t would be 2/3 t plus 3/3 t, so that'd be 5/3 t. Once you do that, let's see, we'll say x1 is equal to, we'll have to add the 4 to both sides, so that'll be plus 4, and then subtract the 5/3 t. Boy, we made it work, but again, did not space this out particularly well. So as far as the solution is concerned, I'm going to go straight to the second form that we used on the last one. So rather than referring to it as the ordered triple x1, x2, x3, I'm just going to put in what we got for our solution. So x1, that's 4 minus 5/3 t. For x2, we got 2 minus 1/3 t. And then for x3, that was our parameter. We used t for that. This is where, once again, t is going to be an element of the set of all real numbers. And we'll put a little separation here between this problem and our last problem. Now, for this last one, this is not technically a system of equations unless you count one equation as a system of equations. So this one we have x plus 2/5 y minus 1/3 z is equal to 6. first thing we'll do, and we'll try to keep this color scheme consistent this time, the first variable that we have listed is going to be our lead variable. Because we only have one equation, I would expect only one lead variable here. The other two variables are both going to be free variables. So let's grab this pen one more time. We'll point out that our lead variable is going to be x, and that our free variables this time will be y and z. Quick pro tip for anybody who hasn't already picked up on it. When you're writing down your z's, be sure to cross them through the middle. Otherwise they start looking like 2's if you have nice sloppy handwriting like I do. So what we'll do is we'll go ahead and define two parameters this time for y and z. So let's say z is equal to t, and we'll say y is equal to s. The names that you use here are completely trivial. They don't actually have an impact on anything, so don't worry about that. Now with that in mind, let's plug them in to our one equation. This will be x plus 2/5 times y. That'll now be 2/5 times s. Oh boy, and now we see another possible slop here. 2/5 times s. Minus 1/3 times z, but z is going to be substituted as t, and that's going to be equal to 6. I'd like to solve this equation for our lead variable. That'll be x is equal to 6. We'll subtract 2/5 s, and then we'll add 1/3 t to both sides. So if we wanted to make this nice and quick, we can say that the solution of this system would be the set of all ordered triples x, y, z such that x is equal to 6 minus 2/5 s plus 1/3 t, comma. Y is our parameter s, and z is our parameter t. This is where s and t are both elements of the set of real numbers. Now, if you're like me and you're not a huge fan of fractions, there is something else that you can do here to make this a little bit easier. So, second possible solution is to note that because we have fractions in here, it is possible to define our free variables in such a way where we can clear out some of those fractions. So, for example, z has a coefficient of 1/3. It'd be really nice if z were a multiple of 3. So rather than calling it just t, we could call it 3 times t. Notice that y has a coefficient of 2/5. It would be great if we could get that 5 to cancel out. So we can say that y is equal to 5 times s. Now again, this does not prevent the fact that s and t themselves could be fractions. In fact, that's completely allowable in a situation like this. We're just setting this up in such a way where we are going to clear out all of the fractions that are occurring. So 2/5 times what we defined y as, that's 5s, minus 1/3 times what we defined z as, which is 3t. And that's going to be equal to 6. Then, in order to solve this for x, we are going to need to subtract 2s from both sides and add t to both sides. So all that this does for us is it clears out the fractions. We no longer have to worry about dealing with fractions. So the solution in this case would be the set of all ordered triples x, 6 minus 2s plus t, comma y, which is 5s, comma z, which is 3t. This is where s and t are both elements of the set of all real numbers. So more on this in future videos.